and ACM ICPC World Finalist. Now, before we start on the problems, I want to first tell you guys a little bit about our Lord and Savior, XCamp.
Computer science and artificial intelligence are tools that will change the future. XCamp Academy is a community dedicated to inspiring and cultivating the next generation of computer science and artificial intelligence talent. XCamp Academy was founded in August 2017 in Silicon Valley by 2 Google software engineers. The name XCamp was inspired by the variable X, which represents unlimited opportunities. XCamp's curriculum system and training methodology is inherited from Mr. Xianyou Xu, a Chinese diamond-level international gold medal coach. Our staff here in the US is mostly composed of senior software engineers from tech companies in Silicon Valley and prestigious CS students from top universities. In addition, we have strong support from international and domestic competition winners in our coach team. From beginner-level Python to classic C++ courses and competition honors courses, XCamp's curriculum is designed for students of all different levels. By participating in team-based competitions and facilitating frequent group study sessions, XCamp also fosters an environment of collaboration to build each student's confidence in their ability to code. As of mid-2024, more than 300 XCamp students have reached the USACO Silver Division and above, including 60 in the Platinum Division, and 27 were selected in the US and Canada national camps, out of which 15 were fresh in the 2024 season and 2 were selected for the US national team. In renowned high school contests, Stanford's Procol and UC Berkeley's Calico, and other prestigious US programming competitions, such as the Harvard Programming Invitational, Teams Code, and Lexington Informatics Tournament, XCamp students perform well, and we encourage students from being participants to problem writers and organizers. Our students received 13 MIT offers and many more from Stanford and UC Berkeley, thrilling us all. Here at XCamp, we believe that children have unlimited potential and can change the world through coding.
All right, awesome. Yeah, so as the video mentioned, XCamp has really amazing achievements in USACO. We have over 300 students in silver and above, more than 60 students in platinum and above, 27 finalists, and we had 2 EGOI medalists and 1 IOI gold medalist, Brian Schick, who got 3rd last year. And for our class system, so first we have the on-site camps, which happen during summer and winter. It's in the Bay Area. It's going to be around 5 to 10 days, and it just depends on if it's like winter or summer, and also depends on what division you're in. We also have year-round weekend classes. We have 4 quarters per year, and these are going to be 10 weeks per quarter. We also have the USACO mock test classes. This happens through during the USACO season. It'll be 4 hours, so roughly 3 to 4 hours for the actual mock test, followed by 1 hour of lecturing afterwards. And we also have the Grandmaster classes for advanced students in USACO Gold, Platinum, Camp, and IOI. And finally, we have the APCS A series. For the February contest, we have 3 problems. The first one is best use function. The knowledge required here is like functional graphs and dynamic programming. And this is covered pretty extensively. Dynamic programming is covered very extensively in the 401 class. And then we have the 602P and 602H class, which is for which is targeting like basically gold topics and training. For the best sequence, this was the algorithm's not too hard. It's just binary search basically, but then the implementation is the really tricky part. And binary search is covered pretty extensively at 400H. And finally, we have friendship editing, which is a bitmask dynamic programming problem. And again, that's covered mostly in 401H, and then also in 602P and 602H. Okay, let's go ahead and take a look at the problems we had. And I'll go in order of in my opinion, difficulty. Uh, so first we have problem one, Bessie's function. So in this problem, we're given like an array, and this array tells us essentially like where to go next. So that immediately shouts functional graph. Because essentially, yeah, let's just take a look at our sample here. We have like 2, 4, 4, 5, 3. That's telling you that this element should go to index 2. This element should go to 4. This should go to 4. This should go to 5, and this should go to 3. Okay. And then there's this part which is a little bit weird, like idempotent. You don't really need to know what that means, but basically it's just like after you make one move, if you move again, you should stay in place. Yeah, and we want to change this array in the minimum number of times such that this array is actually idempotent. So after one move, if you move again, you're like back to like where you are. Or basically on the second move, you don't move. Is one way to kind of think about it. All right, and the first observation probably is that if you were ever to change an element, you should always just change it to itself. So I know that here for the sample, it says you can change a of 1 to 4, but if you think about it, like it doesn't hurt to just change a of 1 to 1, right? And you can also get an answer of 3. So you can change 1 to 1, you could change 4 to 1 or 4 to 4, and then you could change 5 to 5. And this would be an array that's idempotent. I should put this red. Because if you start from 1, you just go to itself. If you start from 2, you go to 4, and then 4 goes to itself. You can start from 3, you go to 4, and then 4 goes to itself. 4 just goes to itself, and then finally 5 goes to 4, and then to 4. So that, yeah, this works great. Or sorry, 5 just goes to itself, and then stuff. And yeah, so this is one solution that works as well with an answer of 3. Yeah. Now, if we look at the additional, or if we look at the breakdown of our test cases, there are some like interesting properties, right? So first of all, we have like a is less than or equal to 20. That suggests we can probably just do some like very big force approach. We have some input where a of I is greater than or equal to I, which it's not immediately obvious why this matters, but I'll get to that in a second. And then we have another set of inputs where all of a of i's are distinct. Okay, so this one's probably easier to reason about how that's important or special. So if all a of i's are distinct, then not only do we get like a functional graph, right? We specifically get like a functional graph that came from a permutation. And what that means is, okay, so yeah, so if all AIs are distinct, then that means we have a permutation. And then we have a permutation like where to go next. Not only do you have a guarantee of every single node has one single out degree, so like the singular node you're supposed to like, the edge you're supposed to follow, it's also guaranteed that every single node has exactly one in degree. And yeah, I guess if this fact's not obvious, let's just go through some permutations real quick. So suppose you have like 1, 2, 3, 4, everyone's just pointing to itself, right? And you're done. Now, suppose I were to swap some elements, like 1 and 3 get swapped. Well, basically 2 points to itself, 1 points to this points to here, and then this points to here, and this points to here. And again, the point is just like whenever you swap numbers, you're just creating a cycle where every node could just go around in the cycle and then eventually get back to itself. Yeah, so let's just start with this this special case where we have a permutation, and therefore we just basically get a bunch of cycles. Okay, let's just deal with one cycle here, and then we'll go from here. So suppose I have something like this. And of course, the trivial case is just like, if you have one node point to itself, this is solved with the cost of 0. If you have 2 nodes that point to like each other like this, you can of course solve this with 1. And then if you have something like this, if you have a cycle length 3, like you can solve it by, I think you have to take 2, right? Like you can fix this node and you can fix this node. For example, I don't think it's doable with 1 because if you just fix one node, then like this node would go twice. Yeah. So this answer would just be 2. And you can probably just like do some analysis and come up with a formula for how to solve this. Um, and then this basically boils down into like decomposing it into cycles. And then for every cycle length, you can like pre-compute an answer if you want, or just calculate on the fly what's the answer to every single cycle length. And yeah, figure it out from there. Okay. And I guess let me give a generalized way to compute the answer for cycles. So what having an edge in this problem means is, well, currently your node is not going to itself, right? So if you have an edge to yourself, then this node is just like always fine, right? If you have a node pointing to another node, that means one of two things have to happen. Either you need to change this edge so that you point to yourself. In that case, this node is now fixed. Like, okay. The only other thing you can do is if you choose not to change this edge is you have to make sure whatever node is pointing towards has an edge to itself, right? Because again, if you like don't change this edge, then once you walk once to your next node, when you walk again, you have to go back to this node for it to be satisfying our idempotent property. Cool. So then essentially one way to solve this problem is, well, let's just think about it as, and this is a common approach as well for cycles, is you just try to break it into an array, right? So can we solve this version of the problem where everything's just like that? Well, of course, this is a very like standard DP of what's the minimum number of elements you need to take such that, like, yeah, such that like one of these two are taken, one of these two are taken, and so on and so forth. So let's say you choose not to take this, you're forced to take this, right? If you choose to take this, then you're no longer forced to choose this. So you can just do some DP of like m by 2, where your state is just what element are you considering? And then you have like a 0 or 1 for, am I forced to take this element or am I free to skip this element? And if you're forced to take the element, you just take it, and then whatever node you point to, or all the nodes that point to you are not forced to be taken, and yeah. Or if you choose not to take the current element, then all the nodes that point to you have to be taken, right? So I guess it makes more sense to go from right to left. So if I pick this node, so first of all, this node has to be picked. And then I have a choice if I want to take or skip. And then for this node, if I like took this node, I again have a choice of take or skip. But if I chose not to take this node, I have to take this node, and so on and so forth. So you can just do your DP like that. Now, how do we go back to the cycle version? Well, if we think about any node, there's only two choices, right? Like in the optimal solution, we either take this node or we don't. Okay, so let's assume I do take this node. I can compute the answer on the rest of this because this is now just the array version. Now, let's say I choose not to take this node. I once again decompose it into the array version because that means I'm forced to take whatever node it points to. Is there a possible greedy solution? Yeah, I think for the cycle case, you can greedy it. Yeah, like if you know the structure is just the cycles, then you can just, and then you just have to take like half of them, round it up, right? Yeah, sounds right for cycles. So like, suppose you have like a cycle of length 6, you have to take like every other node, right? So you just take like this node, this node, this node, and then you're good. And you have a length 7 cycle, you have to take 4 nodes so that they're all good. So we're talking about the special test case here. Special test cases 10 through 15, where you only have like cycles. Yeah, but but the DP is just to like pave the way for the rest of the solution. Yeah, okay, so anyways, the main idea with our DP and decomposing a cycle back into the array problem is that for a given node, you either take it or not in the optimal solution, so you just try both. Like I'm gonna try taking this node, I compute my answer, and I try not taking this node, which means I must take this node, I compute an answer, and then the max or the best among those two answers is the real answer, right? Okay, so that's how we're gonna solve just cycles. And again, you don't actually have to do any DP yet, because you can just greedily figure out the answer for every cycle length and then add them all up. Cool. So that gives you a solid number of test cases. Now let's look at the case where each a of I is greater than or equal to I. So like this seems like a pretty arbitrary constraint that doesn't really help us that much. Well, what this tells us though is that basically the only cycles you can get is of length 1, right? So for this node, you can like point to any node to the right of you. So let's say you point to this one. For this node, again, you can point to any node to the right of you. Then you point at this one, this points to this, whatever. The only way you get cycles is if you point to yourself, right? And so essentially we have like a tree-ish structure, and you're guaranteed at least the last node is going to point to itself. So let's just go ahead and write this out. So this node here maps to this, and this node is pointing to it. This node maps to this, and then this node is pointing to it, and this node is pointing to that. All right. And then finally, we have another one here where this node is pointing that. And the reason why I can get a tree-looking structure is because let me just adjust this a little bit. If you have this node point to this one as well, then you end up with this, right? And let me just label some numbers so that we're figure out what is mapping to what. This is 6, this is 5, this is 4, pointing to itself. Oops, I did 2 4s. All right, so there's 3, 4, 5, 6, 7. So here's 7, here's 6, here's 5, here's 4 pointing to that, and then here's 1. Yeah, and then here's 3, here's 2. So now you basically get a tree, or a bunch of trees. And for each tree, you get the root node for free because it's pointing to itself. And then you just run a very classic tree DP of like, what's the minimum number of nodes you have to take such that either the current node is taken or the parent node is taken. So here you would actually need to do DP. And your state is like, for this current node, am I forced to take it or not? And then the transition is either I take it or I don't, right? So if you're forced to take it, you have to take it. And then your children are not forced to take it, to take themselves. But if you're not forced to take yourself, then you can do either. So then you can just, instead you can just skip the current node and then your children are forced to take themselves. Right. Cool. So yeah, just run this tree DP and then you're done. Now let's go ahead and try to merge the two solutions together. So in an arbitrary functional graph, you can have a bunch of cycles, and then you basically have trees leading into the cycles in a sense. Let me just draw, I'll just draw a smaller cycle here, 3 nodes. But you might have like some tree-ish structure like this. Okay. We might have some part here, but then maybe this node is just alone. Now it turns out we can just do the like DP already talked about for the cycle case. So if you consider, and first of all, just split all the cycles, conceptually just split all the cycles on their own. So like this is a cycle, and then maybe you have like another cycle out here that you solve separately. And yeah, we'll just solve each cycle on its own. All right. So consider any node on the cycle. You're either going to take that node or you're not going to take that node in the final solution, right? And let's suppose I decide to skip this node, but I take this node and I take this node. Well, this is going to give us one solution. Because what we can do now is I can just run the DP. So now consider every tree separately. So I already know I'm skipping this node. So therefore, I just want to find the DP of this tree where the root node is skipped. I already know I'm taking this node, I'm taking this node. So for this tree, I'm just going to run the DP where the root node is taken and find the minimum number of nodes we have to take, right? Okay. So then this would essentially work. So basically for every node, you have a cost to take it and you have a cost to skip it. And where this comes from is, well, if you were to take this node, what's the cost to take all the nodes within his tree, or like to make sure every node in his tree is happy? And if you were to skip this node, then of course you don't pay the 1 for this node, but then you might pay a higher amount to make all the nodes in a tree happy, right? So you can conceptually think about that as like you pre-compute the values for like for each subtree or for each tree. What's the answer if you take? What's the answer if you skip the original node? Okay, and then like root node. Yeah, and then on top of that, you can just run the cycle DP we talked about, where it's like, suppose I skip this node, then I'm forced to take this node, and then this turns into just the array version, right? Because if you have a bunch of nodes in your cycle, and you skip this and you take this, then basically you have the array version where you just need to solve up to here. Okay. Yeah, and then the other possible solution is you can just, you take this node, and then again, it simplifies down into an array version because you can just solve the array up to here. And this is the end of your array. I guess technically, like this would be the end of your array because you're not. Wait, sorry. Yeah, this you start here and you go here because you're not forced to take this. But it doesn't really matter. The main point is just that like you split it into an array, and this is like your start. This is your end. And you just solve array version, and you're good to go. Yeah, so conceptually, that's all you need to do, right? Pre-compute the answer for if you take the root node or not for each node in the cycle. And then just run another DP where you just break up the cycle into an array by like forcing yourself to take a node or forcing yourself not to take a node. And that's the solution. You know, in terms of like a little bit of implementation and overall the solution is just O of n, right? Because every part is just O of n. So first you start by computing your cycles in your trees. And that's O of n. You can just run top sort. And then afterwards, you do your tree DP, O of n total, and then you do your cycle DP, which is O of n, like total as well. Now, you can actually not explicitly do the tree DP. The reason is because once you, or like the cycle, or like you don't actually have to do 2 separate DPs. The reason is once you cut off one edge, which is what you're doing by forcing yourself to take a node or not. Let me just draw it here. So suppose I choose to take this node. Then what that means is this edge does not need to exist anymore, right? Because you can just say this node is already satisfied, for example, right? And that like, so if basically if I take this node, like this node can do whatever it wants, but like this edge no longer needs to exist. So then what you can do is you actually just get a tree now, right? So once you remove one edge from the graph, you just have the tree version. And this is your root because that's the node you like took essentially. And you can just solve the tree version on this problem. Yeah, the tree version of this problem. And then the alternative is if you skip this node, then you're forced to take this node. And then once again, this edge does not need to exist. And you're back down to another tree version here. And so you just solve the problem on that tree. And you take the best of the 2 answers. And that's it. Any questions for problem 1? Okay. Let's go ahead and talk about problem 2 here. Yeah, so for problem 2, you're given a binary string, but you're not just given the binary string, they give it to you in a slightly weird format where they tell you the binary string starts with n zeros. So I'm just gonna draw out the sample here. So you start with n zeros, and in this case 5, and then you're gonna go ahead and basically range XOR certain portions or like toggle certain portions. So the first thing we do here is we toggle everything in the range 1 to 5, so you just get 5 ones. And then you toggle everything from 2 to 4, so then this becomes 1 0 0 1 or 0 1. And then you toggle the 3 to 3 range, so this becomes 1 0 1 0 1. And this is your final binary string. And then now you need to answer 100 queries on this binary string. So I guess let's just start with how do you compute this binary string? And I'm going to do everything assuming n is reasonable, like reasonably small, like 2 times 10 to the 5, which is up to like, which gives you a solid number of points. Yeah, so I'll go over the whole problem, assuming n is relatively small, and then we'll talk about how to deal with large n, because conceptually it's not that different. It's just like really hard to implement potentially. Uh, So to start, we just generate the string by doing like XOR prefix sums or like XOR difference array, essentially. So if you need to like XOR a section of your string, you can just like, let's say I want to XOR this part. Then I can just XOR the first element and XOR the last element. And that basically does XORing the whole part after I do like a prefix sums of XORs. Okay. So let me just go through our example here. So our indices are, let's just say 1, 2, 3, 4, 5, 6. For the first query of 1 to 5, I'm going to XOR here, and I'm going to XOR here. Yeah, this is basically supply. And then for the full version, you have the supply. Yeah. And then our next one is 2 to 4. So I'm going to XOR here, and I'm going to XOR here. And then I have 3 to 3. So I'm going to XOR here, and I'm going to XOR here. This example is not that great. So let me add one more. Let's say you also like XOR the range 2 through 4. Then for here, I'm going to do another XOR on 2 and another XOR on 5. And let's just see what our final result is. So you get 1, you XOR this, still 1, XOR here, 0, XOR here, back to 1, XOR here, still 1, and then XOR here. But this last one is like not a thing. Okay. So your final string would be 1, 1, 0, 1, 1. And that's in fact what you get if you were to XOR all of these queries plus a 2 to 4 rate, right? So this lets us pre-compute what our actual string is after all the XORs in O of n. And now we can just work on the actual binary string as if it was given in the input. Okay, now how do we answer these like queries? So let's say let's just say this is our binary string. Right? So suppose I'm querying this section and I would like k equals 3. Well, first of all, we just count up how many ones there are. And if there's enough ones, then we're just going to pick only ones, right? Now, what if there's not enough ones? So let's say k is now equal to 4. Well, we're going to put as many ones in the front as we can, right? So in this case, we can go like 1, 1, 1 followed by 0. So the algorithm itself is relatively simple. You just want to greedily put all the ones in the front. And then if you need to fill in zeros, you just fill the zeros towards the end as much as you can. Yeah, so there's like a few ways you can think about it. Another way is like you just think about it as you start by counting ones, then you go from the right end to the left. So you go from right to left, and you add in as like few zeros as you can to get to your number k. Okay, and so if you just naively implement this, then you get the test case 4 and you get test cases 6 and 7. Because this runs in like O of n plus m to pre-compute where your string is, and then it runs in O of n times q because you're doing O of n work per query. Okay, so now let's try to get the full solve on 2 times 10 to the 5. Well, it's not that tricky because so let's just analyze our greedy a little bit of like, you take as many ones as you can, and then you fill zeros if you have to, right? So we can start by just querying how many ones are in the string. This you can do with like prefix sums, right? Just prefix sums of all the, just do prefix sums of your array, and that tells you now, like within a range, how many ones there are. Now, if the number of ones is equal or more than k, then you're just done, right? You just output all ones. And if it's not, then what you need to do is you just binary search for how many zeros you need from the end. So essentially, like in this case, if k is 4, then I know I need 1 0. So I can binary search on the end of my string to find, oh, like I just need to include this. And then I can fill all ones, right? Let's say k was 5, then we need 2 zeros. So I can just binary search on the end of my string to find, okay, this part of my string gives you the 2 zeros, and then you can just fill the rest with ones. Cool. So now let's talk about how do we like know what this part of the string is in binary and or like interpret it as a binary number and mod it by like 10 to the 9 plus 7. So the first thing is, if you want a big range of ones, it's actually relatively simple to do this. So suppose I want like 1, 1, 1, 1, 1. Like this binary number, well, I could go through it, add a 1, add a 2, add a 4, add a 8, and add a 16 together to get this value. But a much easier way is I can just take 2 to the power of 5 here, which is 32. And I can subtract by 1 to get 31, which is equal to this. And the idea here is like, if you take 2 to the power something, you're just shifting the a1 to the left and appending zeros, right? So if I take 2 to the power 5, I'm basically adding 5 zeros to the end. And then if I subtract 1 from this, I get like a big range of ones, right? And now if I want to shift this range of ones to the left and append some zeros at the end, again, I just need to multiply by 2 to the power of how many zeros I'm adding. So that's just some like, yeah, that's just how we can manipulate ranges of ones and generally district. Okay, now how do we do this part where I need a query for this substring? What is its binary, or like what does this evaluate to in binary, right? So now what you can do is you can pre-compute like a similar-ish prefix something, where for every single element from right to left, what you can do is you can multiply this by 1, multiply this by 2, multiply this by 4, so on and so forth. And then you also prefix sum that. So now when I take this section in the prefix sums, it's this element multiplied by 16, this element multiplied by 32, this element times 64, and this element times 128. Now, I want to basically shift the 0, 1, 1, 0 back to the, so that there are no trailing zeros at the end here. So what I can do now is I can just divide whatever this result is by the number of positions I want to shift. So yeah, to get this, I can just take this and divide it by 2 to the power of 4. And a little bit on like mod math. So if you want to divide it under mod, you basically take the mod inverse of this. So you first compute 2 to the power 4, which you can do with FastPal. And then you want to take 2 to the power 4 to the power of m minus 2, and that's going to be the inverse. And if you're curious as to why that's true, feel free to just search that up. Yeah. So you do this to get the inverse, and then you just multiply by the inverse, and that's equivalent to dividing. Okay, so now we've got all the parts we need to solve this for n equals 2 times 10 to the 5, right? So step 1, we construct our string. Step 2, we pre-compute a prefix sums. Step 3, for every single query, we binary search to figure out the range of string that we need. And then we have our pre-computed like sum thing that we can take the prefix sums of as well and divide to just isolate out this part. And now we need to append some number of ones to this. So again, you just generate your ones with the technique we talked about. So if you want 4 ones in a row, just take 2 to the power of 4 minus 1. That gives you your 4 ones in a row. And then you should go ahead and multiply this by this length. So in this case, 2 to the power of 4 again. And that gives you like 1, 1, 1, 1, 0, 0, 0, 0 as a value. Yeah, and then you just add this onto this, and that's your final result. And that's how you can output queries in nlog. Any questions about any part before I move on to the like full solution? Okay, so full solution is honestly not that different. It's just the exact same thing, but every single part you need to deal with like coordinate compression essentially. So let's start with constructing our string. So if our string is really, really long, like up to 10 to the 9, well, then whenever you XOR your ranges, you can't just create like a huge array and XOR the first element and then XOR the last element plus 1. Instead, we can go ahead and do this with the coordinate compression / sweepline. And the easiest way is you probably just draw like a map. So this is the index of your array. conceptually. And then this is the value of your array. Yeah. And then the point is, by default, it's just zeros. So this works really well for our array representation. But now the map size only goes up to 2 times m at worst. Okay. And so we still just do the same thing. You like XOR at, let me just call this array. So you take array of L and you XOR it by 1. And then you take array of like R plus 1 and you XOR it by 1 as well. And after you've done all your XORs to construct your actual like binary number, you can just loop through this map from left to right, which is just the default ordering. And then you can pre-compute what your string looks like. So let's say your string's like 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1. Then you basically want to turn this into the following array. So, and you can play around with the implementation however you like. But one way is you store what is in one array. You store the value. So I'll just call that like the B array. So the first element is 0, and then I'm also going to store like a start and end. And I'll just go ahead and 0 next this. Okay, so the start of this range is at 0. The end of this range is at 2. For our next range, it's a 1. The start of this range is at 2. The end of this range is a 5. And these are inclusive, exclusive. But again, you don't have to do this. It's just, personally, I find that pretty convenient and pretty good. And then you have another 0. So this is just 5, 6, 1, 6, 2, 10. And then you have 0 again. From 10 to 13, and then you have 1 from 13 to 14. Okay. And so this is a more compact representation of your actual binary string, where for every section of zeros or ones, you basically just store what is it, and then where does this start, where does this end? And now it turns out we can still do our prefix sums. And again, it's up to you how you want to do this. What I did was like prefix sums up to this point, but not including this section. So this starts at 0. This is also 0. And then up to this point, but not including the section would be 3, because like up to here, basically, is what this corresponds to. For this one, it would still be 3. And then for this one, it'd be 5. That's all. So, okay. And yeah, so now the idea is if you're trying to query the prefix sums of some section from 0 to whatever, so let's just take a concrete example. So suppose you're taking the range from 0 to like 6, right? So it's like, this should return 4 somehow. Well, the first thing you can do is you can just binary search on the end array. And specifically, you just do like lower bound of 6. And that'll tell you, okay, we are here, right? And whenever you're here, that means you can take everything up to here, but not including this new section, right? So it's like this section. So everything up to here is 3 as stored here. And now you can just do a little bit of calculations for, all right, how much more am I taking? And the math there is basically just, or sorry, this should be 7. 0 to 7. That. So lower bound gets you to here. And then so you first just have 3 because you take everything before it, which is 3. And then what you do now is you realize, okay, so if my value is 7, and this range of like ones is ending at 8, I don't know why I wrote 10 before. So this range of ones is ending at 8. Then what that means is I have one more 1 in this section, right? So you can just do the end range minus your R query, and you know that there's one more 1. And so that's how you can get that there are 4 ones in this range, right? And so now we can do our prefix sums query just like before, except the runtime is like log n. Cool. So everything so far is basically the exact same. And then now the final part we need to deal with is something very similar for the, you want to pre-compute the sum of like the the sum of the substring essentially from the end. So similarly, you just have this be like 1, this be like times 2, this be times 4, this be times 8, and so on and so forth. I think we should do a very similar trick. So for every section of zeros, of course, it contributes 0. For every section of ones, you first calculate what the string is. So let's say you have 5 ones. And so, yeah, so let's say you have a 1. This is a value. It starts at index 100, and it ends at index 112. Then you know that this is 11 one or 12 ones in a row. So you first compute that with 2 to the power of 12 minus 1. And then you got to shift by however much n minus e is. So in this case, yeah, so you just shift by 2 to the power of n minus e. So let's say n is like 1,000,000, then you just multiply by 2 to the power of n minus e. And that's how much it would contribute to the suffix sums, essentially. Yeah. And then finally, to query any arbitrary section, you just do the very similar math to the prefix sum thing, except on the suffix. So you first grab everything you can, and then you grab the little extra bits, which you need to compute separately. And that gives you the range sum here. And then you do the exact same thing where you shift it all the way to the right, and then you add on your range of ones. So that part doesn't change at all. Right. Okay, any questions on the full solution? And overall, this runtime is O of n log m to pre-compute your string and this thingy. And then for every single query, you run binary search. So that's going to be log n in the number of iterations. And then for each iteration, it takes log m time to solve it. So overall runtime is m log m plus q log n log m. Overall, you can just say it's roughly m times log squared. Right. Okay, so let's go over to problem 3. Yeah, this one was pretty interesting. So I kind of went down like an unfortunate rabbit hole, but that's okay. So the main thing is just identifying what structures of graphs work, right? Like what does a good graph look like? And then what's the minimal number of operations to turn our current graph into any graph that's good? And right off the bat, the most obvious case is if your graph is empty, like no edges, then of course it works. Another obvious case is if every single node connects to every single other node. So if you have a clique, that of course also works. Now from here, it's pretty tricky to like figure out like what's something else that works. And after a while, you might realize, oh, if you have a complete bipartite graph, that also works. So what is a complete bipartite graph? That's if you have, if you split the nodes into 2 sections, left and right, and every node on the left side is connected to every node on the right side. And if you're on the same side, you have to not connect to your neighbors, like to the nodes of your same side. So let's examine why. So first of all, any edge is going across like this side and this side. And why is it guaranteed that every edge is good? Well, so you have this edge, which has one node on the left. Now, remember, every node on the left is connected to every node on the right, and every node on the right is connected to every node on the left. So then you're good because this node covers all B's, and this node covers all B's. So any edge that's from one side to the other will be a good edge, and therefore you can split it into some complete bipartite graph. It's guaranteed to be good. From here, it's kind of hard to like, and then if you implement this, you can like 8 test cases or something like that. Oh, so it's like decent, but then it's kind of tricky to figure out like, why is this wrong? Like this seems to cover most cases. And so what you can do from here is just figure out like cases that's not a complete bipartite graph that also work. And one idea is like, well, what if I just add some arbitrary node and this node is connected to every single node? Like, well, okay, this is no longer our complete bipartite graph because if I put this node on the left side, it would also have edges to these nodes. And similarly, if I put it on the right side, it would have edges to these nodes. thus breaking our bipartite structure. Um, yeah, and one way you might try to deal with this is, well, okay, what if I fix the subset of nodes that are going to be complete nodes, meaning they are matched at all other nodes. And then I have this complete bipartite structure, right? So I just allow some nodes to be connected to everyone. And then this gives you more test cases, but it's also still wrong. And yeah, so it turns out at the end, it doesn't have to be bipartite at all. You can split into as many groups as you want. Now, there's one very important caveat, and this actually covers all cases, which is, let's say I split some group like this. I have 4 nodes here. I have like 2 nodes here. I have another group of 3 nodes here. And I have like 2 more nodes here. Okay. What I'm going to claim is, for every single node, you need to be connected to every node not in your group. And every node that's in your group, you have to not be connected to them. And let's go through why this works. Well, okay, so first of all, if I take an arbitrary edge, because again, every edge now connects 2 nodes from different groups that you split them into, right? Well, this node is connected to all other nodes, and this node is connected to all other nodes, and therefore this edge is good, right? Because basically from this node, the only thing you were missing is the edges to this node or to this group, and then this other node will cover it, right? And now why is it a problem if you have an edge like this? Let's say you have this edge. Well, the problem is if you have an edge between 2 nodes in the same group, then they're not covering the other nodes in that group, right? Because like this node's connected to everyone that's not in this group. This node's connected to everyone not in this group, but no one's connecting to the 2 other nodes that are in this group, right? So it turns out our final optimal structure is you split your nodes into as many groups as you want. Every group has to have no edges within the nodes in its group, and every node needs to be connected to every node outside its group. And this also takes care of like empty cases or like the whole graph is connected very simply. Why? Because let's say you want the graph to be empty of edges, then you just put everyone into the same group, and now you have no edges. Let's say you want everyone to be connected to everyone else, then you just put every node in its own group, and every node is now connected to everyone else. So basically, any possible optimal structure can be like subdivided into some like subsections of groups. Okay, so now we can have like a brute force solution that's n to the power of n, because there's at most n groups, and then for every node, you just choose which group does it go into, and that runs in O of n to the power of n. Assuming you can also very quickly do the check. And finally, to speed this up, we're going to do some bitmass DP. So essentially, initially, you have all your nodes are not part of a group, conceptually. And then what you're going to do is you're just going to pick some subset of them and move them into a group. So let's say I pick 1, 2, and 4 and move them into a group. Well, what you're going to notice is I can directly calculate the answer, or like this part of the answer. Because if there's any edges between 1, 2, and 4, I have to remove them, and that incurs some cost. Our other part of the cost is, for node 1, you can loop to all other nodes, and if you don't have an edge, that's another cost. For node 2, same thing, loop to all other nodes. If you don't have an edge, incur a cost. And node 4, if you don't have an edge, incur a cost, right? Cool. So when I split this group, it actually doesn't matter what the other groups are. I can directly compute the cost to make this group, right? Because regardless of what the other splits look like, every pair of nodes in this group have to have not an edge between each other, and they must have an edge to all other nodes, right? Okay, so then when I split this group, I can go ahead and add that cost to the DP. And so now my state is just DP of like some bit mask of nodes that have not been split yet equals the minimum cost to split them. And you can do this multiple ways. Like your mask can represent which nodes have been like put in a group, and then the min cost to get to this state. But regardless, at the end, you either output DP of 0 or you output DP of like full mask -1. So to the power of n -1. Okay. Yeah, so that's our DP. And our transition is you just move through all the possible subsets you could now do. And this naively sounds like O of n to the 4, or sorry, 4 to the n. Because you have 2 to the power of n states, no doubt about that. And then the number of transitions seems to be 2 to the power of n, because for every subset, or like for every subset of nodes, you're going to loop through all its subsets. But it turns out, and you guys might already know this overall runtime, if you implement it efficiently and only loop through the submasks, becomes 3 to the power of n. Conceptually, one way to think about this is for every digit, so there's n digits. For every digit, there's only 3 possibilities. If you loop through all masks and all submasks. Let's say for this digit, in your mask, it's a 1. Then, or let's say in this digit, in your like mask, it's a 0. Then in the submask, it has to be 0. But if it's a 1, then it can be a 0 or a 1. Right. So for every digit, there's only 3 possible combinations. The case where it's not in your original mask, but it's in your submask is impossible, because that would not be a submask by definition. So you just have 3 to the n if you loop through all masks and all submasks of that. Yeah. And overall, now our runtime is just O of 3 to the power of n. But you need to make sure you pre-compute your costs for each group. And you can do this in 2 to the power of n times n squared. Okay. So basically for every subset, you just pre-compute, like if I choose this subset, what is the cost? And again, you can just naively loop through all pairs of nodes. And then if a pair is like both in the group, then if they have an edge, you increase the cost. If a pair of nodes is like one in the group, one not in the group, then you incur cost if they don't have an edge. And then if you're looping against like nodes that are both outside the group, then it doesn't matter. Right? So that pre-compute is just 2 to the power of n times n squared. And now you know whenever you pick a group, what is the cost to pick that group. So now you can do all your DP transitions in O of 1, and you have a total of 3 to the power of n transition and 2 to the power of n states. And that's how we get our overall runtime of 3 to the power of n plus 2 to the power of n times n squared. And this works 5 for 16. And if it was 17, it would not work. So another, I guess, possible takeaway here is, so I guess like most people know that if n is small, like around less than 24, or usually it's going to be less than or equal to 20, this kind of shouts bitmask, right? But even more fine-grained, like if n is less than or equal to 16, this kind of shouts subsets, like submask little masks. So it suggests, so first of all, 3 to the n works, and 3 to the power of n times n also works if you're careful about constant factors. But anyways, this suggests that like you probably want to loop all like masks and then potentially all submasks, the masks. Yeah. And then you have your other common one for like 10, which is just like n factorial. Right. Or I guess like 8 unit. Well, the question for this problem is to choose a node and choose all two to the power n combinations neighbors. The entire graph is decided because for each connected chosen node, this should generate, but it doesn't work. Okay, okay. Yeah, so basically if you pick a starting node and then you pick who they, okay. Yeah, so if you think about the current solution we're doing, we can actually map what you're doing with that, right? So let's say this is node 1, and you pick the subset of nodes. Let's say you pick 2 and 3 to be, let's say you pick 2, 3, 4, and you don't pick 5 and 6. Then in terms of our current solution, I assume the official solution, then that means you're putting 1, 5, and 6 into a group essentially. And now, like, no matter how 2, 3, and 4 are distributed, like 1 is connected to all of them. But this doesn't uniquely guarantee what your graph ends up being, because you still can decide how to group together 2, 3, and 4, right? Like your answer is going to be different if you now decide to group 2 and 3 together, versus if you try to just group 2 and 4 together. Like this would be a different solution from 2, 3, 4 in separate groups. So basically that's why this is just picking the subset of edges for the first node, or like an arbitrary node, does not map to one of these solutions, right? Any other questions? Okay, then that concludes the goal problems.